file to the TN and me, okay? And please also print out the hard copy, okay? You can print out the hard copy because I have to make some record when you do the presentation, okay? And then next week I will show about the report list. So you guys should know about what times you need to get the report, okay? And the report time is about 10 minutes, okay? About 10 minutes. And 10 minutes will be including 2 minute Q&A, okay? 2 minute Q&A. So probably approximately 1 minute will be one slide. 1 minute in average, if you do the presentation, average 1 minute, one slide. So this is just take for you guys some reference. And of course, we don't have any page limitation. So if you wanted to prepare more slides or less than 10 slides, it's okay. It will not affect to your score. Okay, so your score. So don't worry about that. But just make sure that if you want to prepare more slides, you still have to finish all the slides within 10 minutes. Okay, and still I would say 8 minutes, and because we have a 2 minute Q&A. So therefore, have to control your presentation.
So should we just send the PPT files by email? Or?
Yeah, by email to me, CC to me, and email to the PA submission. Okay, submission you can send your mail to all you.
Yes,
yeah.
Professor, they know
Okay, yeah, and please also print out the hard copy. Okay, print out hard copy. And for example, if you are not present at the first week, for example, you present third week of the December, and then you may have some update. Okay, and I still not. You guys can send the new update version to me. Okay, so I will use the last version of your presentation. Okay, is that okay? Yeah, so, okay, and next week I will show the list. Okay, yeah. Okay, so today we will finish page chapter 7. Last week we have talked about regarding some of the energy harvesting device. So using mechanical vibration force. So it is the new technology that in the previously, I would say before 10 years ago, the scientists are now aware about how to utilize the such irregular, we call it irregular mechanical energy. So irregular mechanical energy you can find everywhere, right? For example, you can see the vehicle travel on the roadway. It is huge, right? Everywhere has a vehicle to travel in the roadway. So this vehicle applies pressure on the road. So therefore, this is a very high activity. I would say the energy is always there, but we still cannot find the right technology to harvest such pressure, such mechanical pressure in every day, every minute, every second on the road, push into the road. So therefore, this energy is just waste, right? This energy is waste. And in contrast, you can see the largest energy is from the ocean, because the ocean wave, right? Which is the largest. Compared, of course, I would say the solar light is huge, right? The solar light is huge. But now the scientists has been developed put a lot of effort on the solar light. How to utilize the solar light, convert to the electricity, like we have talked about the photovoltaic. We also have to talk about thermal energy, also generated from the sunlight. And then sunlight can do a lot of work. But another way is ocean wave. Ocean wave is any meaning compared to the solar light. Solar light just 1 day, right? Just 1 day, I would say maybe 6 to 8 hours, depends on the geological position and country, right? So maximum will be maybe 8 hours. But for the irregular energy of the ocean wave, that's 24 hours, right? Because of mechanical energy, 24 hours. So if we can find a way or find a technology that can develop to convert such mechanical energy to the electricity, then this will be a huge contribution to the human being. Okay, to the human being. So therefore, I believe, as I remember, in the first chapter, I have shown this slide to you guys, right? So we have put a lot of effort on sustainable macro power. What is the sustainable? Sustainable macro power. Macro power, that means the huge power, right? Like nuclear energy, right? One of the nuclear energy, and also photovoltaic, and also geothermal energy, hydropower. All of them contribute to macro power. Okay, macro power. Macro power is this power can maybe as maybe 1 day can be replaced the traditional fossil fuels, right? So people has less address, okay, less address or less aware about what about some of the low power consumption device, because we have not device for low power consumption, just a portable device and also biosensor, right? Biosensor, and also maybe laptop 1 day, right? So this is also called low power consumption device. So as a low power consumption device, if we look at about the environmental issue, because we have to prepare the battery to this low power consumption device. We have to prepare the battery, right? So you will always need to replace battery and battery. So therefore this battery will become the waste. That's why I have mentioned in last week, so-called the electronics waste. It's huge, it's a huge, I would say maybe a disaster for the next generation, right? So therefore, if 1 day such low power consumption device can be used some cell power device, that means we don't need power, we don't need a battery. So therefore we can save the battery, and there's no need to recycle such battery. And then that will become an eco-friendly product. Okay? So this is I will for the next few slides I will introduce about the nano generator. Okay, so those nano generator can interacting technology. So-called if you have some of the device, maybe you can monitor about the blood pressure and also pulse, right? Pulse, and also a lot. Maybe you can having the device to monitor about your health. Okay, we call it health care. Okay, to assessment and then to justify about your health. Okay, so this is very important. That recently, I would say, 10 years, there's a lot of device that's been produced to monitor such a body temperature, body sugar level, and also this is some of the interacting. Interacting, that means to show you about the real in situ situation about your health. Okay, for example, you don't know about your blood pressure unless you measure, right? So you have to go to, for example, you have such device, and then you can measure in your when you go back, when you go home, right? So you have such instrument to monitor, right? But actually, if our portable device, right, can provide such a functionality, so every minute you can check your blood pressure. Okay. And then the blood pressure sometimes is different. I would say, for example, today I go back to my home, I have a blood pressure instrument. So every day I check using this instrument. So I can know about the saturation, about your blood pressure's difference. But if today you go to the hospital, you measure another blood pressure, the instrument is different. So there is something different, right? So I would say the blood pressure is you have to monitor every day in the same device. You cannot monitor every day in a different device. That would be something different. Okay? So it is quite important to having such device embedded to your, for example, cell phone, smartphone. So your smartphone has such big data. You can correlate all of your health situation, including sensor. Okay, including some of the sensor. This sensor can detecting the gas. All right, the gas something like CO gas, carbon monoxide, and some of the text gas like carbon dioxide. Right, the concentration of the carbon dioxide. For example, in the crowding, there's a huge people crowding in the basement. Maybe carbon dioxide is too much, but we don't know. You don't know, right? So you will feel very tired because the oxygen concentration is low. So you feel very tired sometimes, right? So if you have such a functionality device, and then can always follow with you, and then you can have more information to understand about that. Okay, so all of that, if we prepare the device, one device, one battery, one device, one battery, and then there's a lot of the battery, right? It is become a recycle issue. Okay, so now is this chapter I will introduce about the tribal electrical nanogenerator and piezoelectrical nanogenerator. So the fundamentally is generally come from the Maxwell equation. You know the Maxwell equation, right? This is very traditional developed by Maxwell in 18th century. Okay, you know the current density. Later on, I will show more detail about the D. Okay, D so-called is the electrical displacement. Okay, this electrical displacement, partial electrical displacement, partial P, can be equal to this term. So this term actually is induced electrical field, which is relative to electromagnetic field. Okay, electromagnetic. So this electromagnetic field need to modify by the materials. Okay, what materials you have? Difference. Epsilon is the dielectric constant. Besides, actually, we still have to consider about this term. For the Maxwell equation, only use this term. But Maxwell didn't consider about this term. Okay, later on I will show you what is this term. This term actually is the polarization. Polarization, okay. Polarization, the surface polarization, okay. As a function of the time, we call the partial. Overall, D will be epsilon partial D over partial T plus partial polarization partiality. This term is contributed by non-electrical field, which is induced by material's strength. Okay? So-called if you have materials, whatever, for example, today the materials is from the piezoelectrical materials. And then when you apply the strength to the piezoelectrical materials, which will induce the polarization, right? Induce the polarization. That we call the dipole, right? Dipole moment. Later on, I will show you more detail. So actually, this term also contributes to the current density. All right? So in the previously, people just take this and use, but they're not aware about this term. Actually, this term is contribute quite huge. If you have piezoelectrical materials or triboelectrical materials, there is a polarization. Okay, there is a polarization. I will show you about this. Okay, so this is the major fundamentally issue, how we wanted to introduce this equation to you guys. Okay, the very important for energy harvester device using triboelectrical nanogenerator and piezoelectrical nanogenerator. All of them is contributed by this term. Okay, by this term. So we wanted to explain. This term is quite important because this can generate the current density significantly, and then it depends on the time. Okay, depends on the time. So actually, I would say the Maxwell equation, this term, need to modify to plus this term. Okay, this term, and then this is overall completely Maxwell equation. And this is developed by Professor Zhonglin Wang. Okay, Professor Zhonglin Wang. Last week he has given a primary talk at our basement Okay, so so now it's what is the polarization? Okay, what is the polarization? Okay, so this is I wanted to explain what is the piezoelectrical polarization. I have added some few slides to this chapter, but I didn't send you guys yet. Okay, I just add today. Okay, but I'm not worried about that. I will send you send an update version. Okay, after the class. Okay. So this is I would say this is a similar phenomenon. Okay, similar phenomena. Polarization based on the atomic scale. Okay, you have the proton, right? Surrounding on the proton, we know the atoms has electron cloud surrounding on the atom, right? Surrounding on the atom. So if there is the external field, for example, the green color is an externally, okay, external electrical field. So the external electrical field, the sign is here it will be negative, here it will be positive, right? This is the sign, right? So therefore, under apply the electrical field to this atom will become importing. I draw a more exaggerate rate. Something like that. Right? Because this positive proton will be pulled by this electrical field, right? So similar to this spring, right? Similar to this spring. Here is the spring, okay? Is the spring. And then if there is an object, right, being pulled by the gravity, right, by gravity. And this spring will be pulling, something like that, will be pulled. So the length will be different, right? The length will be different. So usually, if we wanted to calculate about the force, right, about the force, so the force will be this force. This force is equal to K multiplied by X, right? This K is the constant of this spring, right? And S is the deviation, right? How much distance being pulled, right? Being dropped, right? So, same situation if you wanted to calculate about the force, right? But now, what about the polarization? Can we calculate the polarization? How much polarization can be calculated? Completely similar to Newton's law, right? So if I wanted to calculate the polarization, so what is the polarization? Anyone can let me know? I'll give you a bonus, okay? Almost the final.
The displacement of
P.
the proton and the electron at when they are equilibrium. External electric field.
Yeah, so do you have some equation can represent? Actually, the answer is in your slide. Yeah. Last minute.
It's a charge into displacement equals to polarization.
Charge what?
Charge into displacement. It's an equation for the polarization.
Yeah, polarization is equal to charge displacement. Charge displacement, and then
charge into displacement, dipole moment, not polarization.
charge displacement, what?
Charge into displacement, professor, it's dipole moment, not
It's dipole moment,
yeah,
yeah.
it's not a polarization.
It's a dipole moment.
Yeah,
So you are the TA. Yeah, it's okay, yeah. Just recall, yeah. This, recall you and you. Okay. Give you an idea to solution. But almost right, okay. Charge is a so-called, because it is the important, because you guys need to understand about the displacement, right? So this is the displacement as, right? That means the carrier being pulled, right? How much distance, how much displacement, right? Displacement multiplied by charge, right? This is charge. How much charge being pulled, right? Being displaced. So this is the slide right here, right? We call this will be electrical dipole moment, right? Electrical dipole moment, because dipole moment, this is, what is a moment? Moment doesn't mean just like a bending the moment, right? So it depends on the displacement. The large displacement being created, the large polarization will be generated, right? And then Q will be fixed, right? Q is the charge, right? Q is the charge. So the most important term is the X, right? Similar to here, right? Similar to here, as I just mentioned. So this is a electrical field, okay? In electrical field. So you can see electrical displacement when you apply electrical field to it, and you will pull the positive and negative charge will be separated, create a polarization. All right. So all this polarization contribute to this term. Okay, contribute to this term. And previously, people didn't know aware about that. Just use this and take this equation and use it. Okay. So now we have to aware about this term. Okay, we have to aware about this term. So now, for the dielectrical displacement, okay, for the dielectrical displacement, I would like to explain about the dielectrical displacement. So for D, okay, D. For the dielectrical materials, is the electrical insulator that can be polarized by electrical field, right? So for the high dielectric constant, which means you have to apply the higher electrical field. So therefore, you can pull in these materials. Do you understand? For example, you have the dielectrical material. All of the materials has a dielectrical constant. Whatever for the insulator, for the metal. Okay. Usually for the metal, the dielectric constant is very, very small, right? For the insulator, it is a high dielectric constant, right? High dielectric constant. So for the dielectrical materials, you have the positive and negative. Molecular, you have positive and negative, which is then randomly distributed. Okay, randomly distributed. For example, this is one of the dielectric materials, something like that. Okay. But today, if we apply an electrical field, right? Electrical field, then this molecular, okay, whatever for the polymer materials or inorganic materials, their dipole, okay, will be switched to align together under this electrical field, right? So this electrical field negative, positive here. So therefore, this molecular will be positive, negative, positive, negative. For the ideal case. Right? For the ideal case. So under this situation, you can see when a dielectrical material is placed, these materials is being placed under the electrical field. And then the electrical field do not flow through the material as they do in a conductor because this is a dielectrical materials. It's an insulator. But only slightly shift. Okay? It depends on the dielectrical constant. If the dielectric constant is low, then it completely shift. If it is quite high, then I would say molecule is hard to switch. So for example, I ask you, oh, get out. You may not, no, right? So it depends on how force. And people maybe say, okay, I ask one student, hey, get out, and this student right away, right? So this is the strength, right? The strength, okay, something like the strength, okay. 不好意思，我刚刚做了一个不好的比喻，不要介意。So when a dielectric placement in an electrical field, so the electrical charge do not flow through the material as they do in a conductor, but only slightly shift their average equilibrium position. So therefore cause the dielectric polarization. So because the dielectric polarization, positive charge are displaced toward the field and negative charge shift in their opposite position. So this is what we have the difference, because this is positive, negative, this is positive. So therefore it will shift. That means this is positive, this is opposite. Okay, this is opposite. Okay, so next few slides, I just add in. Okay, next few slides I just add in today. Okay, so I will. Okay, I just write on the blackboard. So, for example, in the vacant state, so you have epsilon 0, which means in the vacant state. Okay, in the vacant state, and then if we apply electric field on both electrode, right? So you have the materials, right? This is positive, negative, positive, negative. This molecule is only in the vacant, so we call epsilon 0 is the permittivity. At free space. Okay, at the free space. If today we place another materials, one of the objects, we place one of the dielectric materials to here, right, to the vacant cell. So you will see that this is the electrical field. This is negative, this is positive. So here will be spin, positive, negative, positive. So this green is an electrical field, okay? Is an electrical field. But remember, inside the materials will provide an opposite electrical field, right? An opposite electrical field. Do you understand? So therefore, the total electric field, this total electric field can be written like E in vacant divided by epsilon. This epsilon is the material's epsilon. Permittivity. Okay? Right? Because at the vacant, this is also at the vacant electrical field once divided by the permittivity of this material. So therefore, the overall electrical field will be weakened, right? 弱化, right? Will be weakened electrical field. So this can be write like, okay, E vacant polarization, right? E vacant like this, right? This is E vacant, right? And this is E polarization, right? E polarization. Because overall E will be weakened. Is that okay? Right? And then now, there is a dielectrical displacement. Okay, there is a dielectrical displacement. So dielectrical displacement, that means the materials being polarized. So there is a electrical displacement. Okay, there is an electrical displacement. So, the electric field strength is reduced by insert electrical materials between two capacitor grade. This is just because this is two electron, right? So inside this dielectrical materials become a capacitor, right? Become a capacitor. So overall E is can be read like this. And then second, with the dielectric materials, the electric field strength E is replaced by dielectric displacement. So-called D. This D also called surface charge density. So we can write like D is epsilon real, epsilon multiplied by E. This is also equal to Q over A. A is the surface area. Q is the charge. So now I introduced about the dielectric displacement, which is a result from electrical field strength. Okay, because this is induced by electrical field strength, right? Electric field strength. So at this time we call the dielectric displacement D. Okay? And this can be further to write like this is P. Is that okay? P. Because this is positive, negative, right? So if you look at this, I use in the blue color, okay? Actually, blue color we write like this. This is P. This is P, right? This is P. But the red color is EP. Right? Because EP will be reduced, right? The electrical vacuum will be reduced by EP, right? Simultaneously, actually this has a polarization this way, right? Because the sign of the polarization positive is this way, right? So you have the P this way, right? P. We call this as P. Accordingly, the overall D can be rewrite this term, okay, also equal to epsilon 0, epsilon plus P, right? Plus P. Epsilon 0, epsilon is because of the epsilon 0 is the permittivity at the vacant state, right? Multiplied by epsilon, that means the material's epsilon, right? The material's epsilon. Because you still need to consider about the material's epsilon at the vacant state, right? For example, the material has an epsilon, right? But this improved to the vacant state. Overall vessel epsilon should be epsilon 0 multiplied by epsilon. Understand? Right? So this is the material's epsilon. Right? Material's epsilon. So now let's further to the right. Okay, further to the right about this. This can be right like epsilon 0, epsilon, this is material epsilon. P can be right like epsilon 0 and chi E multiplied by, sorry. Yeah, okay. This is the epsilon. This is E. Right? E. Okay, in the vacant state, this is in the vacant state, okay? In the vacant state. And this is E is the electrical field, okay? Now the big E we call the capital is the electric field. And then here later I show you about this P is also can be read like this term. Chi E is the susceptibility, okay? Susceptibility. Wait a moment, let me show you about what is the susceptibility. 哦，小薇，哎 ，now is shall we take 10 minutes? Okay, later I will show you about this. Finish this. 稍微小的。